Today we have Hank Childs, who is an assistant professor in the Department of Computer and Information Science at the University of Oregon. He received his PhD in computer science from the University of California at Davis in 2006. Hank's research focuses on scientific visualization, high-performance computing, and the intersection of the two. In July of 2012, Hank received the Department of Energy's Early Career Award to research visualization with Exascale computers. Hank spent over a dozen years at Lawrence Berkeley and Lawrence Livermore National Laboratories, directing research in big data visualization. Outside of his research, Hank is best known as the architect of the VISIT project, a visualization application for very large data that is used around the world. Professor Childs' research focuses on visualizing very large data. Recent research results have explored using hybrid parallelism techniques on scientific visualization algorithms, techniques for simplifying very large data sets so they can be more readily understood, and designing visualization algorithms that can scale to tens of thousands of CPUs and beyond. Today he will describe the exascale landscape and how visualization will look different in the future. Hank, the mic is all yours.
Okay, thanks very much, Lorraine. I hope everybody can hear me. And I actually can only see my PowerPoint presentation. So as questions come in, hopefully Lorraine or somebody can speak up and let me know. Lorraine, thanks very much for that introduction and for inviting me to come give this talk. And actually, I do think that exascale visualization is going to look really, really different than what we've been doing before. And the way this presentation will play out will be me describing what are the factors for why it will look different, and kind of explaining to all of you, as we go forward, how we're going to impose on you more and more and justify why we need to do these impositions. My hope is by the end of the presentation, you'll have a better sense of what exascale visualization will look like and what you're going to need to do. And actually, I think it's going to require a lot of partnering. And so we can talk about some about what that partnering will look like for people to be successful at the exascale, at least when it comes to visualization and analysis. So I'm not going to talk about all of these pictures that are up in this initial slide, but I will talk about the one that's in the middle. The middle one, let's see, I think if I do this with my cursor, everyone can see exactly what I'm pointing at. The middle one is a Rayleigh-Taylor instability, and the idea behind a Rayleigh-Taylor instability is that you have a heavy fluid and a light fluid mixing, and so the heavy fluid is here on the top and the light fluid is on the bottom, and it's gravity that pulls the heavy fluid into the light fluid. And so this was a simulation that was run at Lawrence Livermore quite a long time ago, ran in 2006, so that was 8 years ago. And the mesh resolution size was 3,000 by 3,000 by 3,000. So there were 27 billion points on the mesh. And we were just so surprised how big this mesh was. We had only ever seen one mesh before that was more than a billion points. And we thought it was really exciting to be looking at something that was 27 billion points. And if you fast forward to today, you see people doing stuff that's a trillion data points. And at the exascale, of course, it will be much larger still. And so there's big data as a topic that's discussed worldwide, but certainly the data sets that are being visualized and analyzed are getting big at a really astonishing rate. Now, one of the points that I want to make about this data set is that the way we analyzed it will be increasingly hard going forward. And so the way that we analyzed it is pretty typical of how we think about the simulation and process working and the visualization piece. And that's that someone ran a simulation, they saved data to disk, and then afterwards, sometimes people call this post-processing or post-hoc analysis. A visualization program was run. In this case, it was the VISIT program that Lorraine mentioned earlier. To make and we loaded this data from file and made this picture. And then beyond that, there was a group led by Valeria Pascucci, who's now a professor at the University of Utah, that did topological analysis, where they asked the question, how can we define what is a bubble? And a bubble would be one of these things rising up out of the mixing region, or a spike, which would be one of these regions that is sinking down from the mixing region. How can we classify bubbles and spikes and count them over time? And so that was something where a lot of research was required, where people had run the simulation, they looked at the results, they knew that they hadn't asked all the right questions going into the simulation, and there was a period of months where the data was analyzed after the fact. So in the exascale, those opportunities won't exist anymore. It's not going to be possible, or at least it will be very difficult to do that sort of extended analysis after the simulation runs. And so that's one of the takeaways from the talk, and I want to again further justify why that's the case. So as we go through the talk, it'll only be till the very end that I think I'll be able to put the bottom line in terms of what you're losing and how it's going to be more unpleasant than it has been so far. Okay, so here's an outline for the talk. I'll give a background in scientific visualization, high performance computing, and the intersection of the two, and these will be a very quick background. And then I'm going to describe some of the challenges for petascale visualization and then try to contrast them with some of the challenges for exascale visualization. I'll give a quick overview of exascale computing and what some of the challenges will be at the exascale, because it's a very different world than the world we've lived in so far in terms of some of the leading edge supercomputers. And then, of course, what I'm really excited about and want to tell you guys about, and what Lorraine asked me to tell you about, was this exascale visualization problem. So I'll start with a background in scientific visualization. And so, I think this top part of the slide is probably very obvious to all of you that you can think of the simulation process as happening in phases where there's a setup phase, you define boundary conditions, you make a mesh. And then there's a simulation phase, and the simulation produces lots and lots of data, and then people visualize that data. And so it's not always the case that these are done in sequential phases, that you do problem setup and then you do simulation and then you do visualization. But it's a good mental model because that's how it happens a lot of the time. Now, something I do want to point out I think is really important is that visualization is used in three, I think, pretty distinctly different ways. And so as people think about visualization, sometimes one of these three ways is the way they use it most often. And they think about just that one way. But I think all three ways are really important. And so I want to describe what I think these three classes are. The first is that people use visualization for confirmation. So they've run a calculation 1,000 times, they're running it the 1,001st, and they want to make sure the train didn't go off the tracks. The second is the one that I think is really exciting. People don't often use the word sexy with computer science, but I think it's the sexiest of the three ways, and that's that you explore data. You don't know what you want to look at, you don't know what you want to do, and the hope is that after this exploration process, after you go and you ask questions and you get answers and they confirm or deny hypotheses, that you've learned new science, that there's new insights. And so I think that's really exciting that visualization can contribute to that process of advancing science and really helping realize the value of the simulations. The third way is communication, and this is what people often think of when they think of visualization. They think of someone taking a movie and showing it to an audience at a conference. They think about taking an image and putting it in a PowerPoint presentation. They think about putting the image or maybe a 1D XY plot in a journal paper. And so visualization and analysis are really helpful for communicating results to an audience. And so these three different ways of using visualization actually lead to different processing paradigms. And these processing paradigms will be important as we get to the later part of the talk. So I think this slide is one that I typically present just to say that it's important that we have supercomputers, that we need HPC. I suspect this community knows that pretty well. But the notion that we're striving towards an exaflop or striving towards ever greater scales of HPC is sometimes confusing when you talk about machines that have costs of hundreds of millions of dollars. But I think especially for the CIG group, you understand it. There's really not a lot of alternative to simulation. The experiments you can run, well, maybe you can't run them at all. And so you need simulation to be able to ask the questions that you want to ask. And so, of course, by having more compute cycles and more memory, you get faster turnaround time and you get more accurate simulations. And here are three other communities that have similar stories in terms of why, even in the context of machines that cost hundreds of millions of dollars, it's still cost effective. So as this community probably knows pretty well, the way that computers are measured is what's called a flop. So the ability to do one floating point operation per second. My brain is approximately a one flop device. The laptop that I'm giving this presentation on is approximately a 1 gigaflop device. And our community has gone through several milestones. We went through the milestone of having a teraflop in 1998 or 1999. And we had our first petaflop machine in 2009. So that was the ability to do a million gigaflops or a million billion flops. And so what our community is talking about now is an exaflop, which is the ability to do a billion flops. And so I actually need to update this slide with the Chinese machine, which is the new number one. It can do 30 petaflops. But you can see that the machines 2, 3, and 4 are all doing on the order of 10 to about 30 petaflops. So that's where we are as a community today. I've come out of the Department of Energy Labs, as Lorraine mentioned, and so the Department of Energy Labs kind of hit this point in 2008, 2009, where they were asking, do we need to go higher in terms of the compute power that we're providing on our supercomputers? And so there was a series of workshops that were held, and you can see what the 8 workshops were. And each one of the workshops came back with the same result. They said if they had an exaflop of compute power, they could revolutionize their field. They could understand climate change. They could build better nuclear reactors. They could achieve fusion, etc. And so these 8 reports on the Department of Energy end served as a rallying point for the community to talk about how they were going to build this first exaflop machine. But the thing is, it's a lot different than what it has been before. It's not a matter of taking the designs that we've had and just scaling them up to be bigger. We actually have to do things fundamentally different because we're constrained by power limits. And I'll talk about that more later in the talk. So, of course, the Department of Energy is not alone. So Exascale is a movement. For those who have attended the supercomputing conferences, you'll hear about the exascale and exaflops over and over again. And so there was a community that's met, I think they've had on the order of a half dozen to maybe even as many as 10 meetings to discuss how they can possibly build an exascale machine and fit within the power budgets that they have. And they published an often cited paper that kind of describes their thoughts about what an exascale machine would look like and how software is going to have to run on this machine. Okay, so that's a background in scientific visualization and high performance computing. And so let me talk a little bit about an area that's, of course, what I'm really interested in, which is the intersection of the two. And so when you're talking about visualization in an HPC space, you're often talking about really large data sets, big data. And so, of course, big data is a fuzzy term and an overused term at this point, but it's actually pretty easy to define big data when you're talking about visualization. Big data is data that's too big to be processed in its entirety all at one time because it exceeds the available memory. And if you parse that sentence, there's actually 3 clauses in there. It says it's too big, but it said the first clause is that it's to be processed in its entirety. The second clause is that it's to be processed all at one time. And the third is that it's because it exceeds the available memory. And those 3 clauses suggest 3 different approaches. If you don't want to process it in its entirety, then you can think about doing data subsetting, where you only look at a portion of the data, or you can think about multi-resolution techniques, where you look at coarse versions, like a Google Maps type setup. If you don't want to process it all at one time, then you can do streaming or out-of-core techniques where you load in pieces and operate on those pieces and then discard them and load the next piece. And then the third criterion is that it exceeds the available memory. And so, at least in the HPC Viz community, we've all tackled this third criterion and said, aha, we have a supercomputer lying around as the thing that generated the simulation. And if we use this supercomputer and used more and more nodes on the supercomputer, we'd have more and more memory. And so we'd be able to look at these very large data sets. And so it's really through parallelism that we look at a lot of these big data sets today. Again, all of these approaches are good. It's just this last one is the one that our community has focused on. And so we don't just use parallelism, we specifically use data parallelism. And the idea is that if you have a simulation data set that you try to decompose it into pieces, and then you divide those pieces amongst multiple processing elements. And so I use the acronym here PE. And so a processing element is an instance of your program. You may have an instance running on one node, another instance running on another node, and so on. And so each processing element loads its piece of the larger data set and processes it. Ideally, the algorithms that you want to apply require very little coordination between the processing elements. And then ultimately you render it. And so you take the results from each of the processing elements and combine them into a single image as if they'd all been processed together. And so this, again, is the approach that our community has focused on. Now, I submitted an article to this computer magazine call back in May of 2013, and we talked about big data visualization. And one of the reviewers rightfully told me that we really weren't talking about the big data that the rest of the world talks about. And they referred to the big data we do as little b, little d, big data, and the big data the rest of the world does is big B, big D, big data. And the point that they made, which I agree with, is that we're in the Viz community are focusing on large homogeneous arrays. We're reading them from a parallel disk, and we have symmetric resources. And a lot of other communities are talking about capital B, capital D big data, are talking about heterogeneous unstructured data located in a distributed setting and processed with asymmetric resources. And so, we're solving a hard problem, but it's a hard problem that's different than this other hard problem that a lot of the big data community is looking at. And it's not that there aren't lessons learned that can be passed between the two, but it's worth noting that they are different. So how far can data parallelism go, this approach that we're using? It actually can go pretty far. And so I led a study a few years ago where we wanted to look at tomorrow's problems and understand what the bottlenecks were. And we scaled some data up so that there would be trillions of data points in the mesh, trillions of mesh resolution points, and used tens of thousands of cores. And we found that the data parallelism approach is really a good one, but that I/O is a limiting factor. And this I/O being a limiting factor is actually a theme throughout the talk. Okay, so a quick outline. So we're back to the outline, and I want to talk some about petascale visualization. I just want to ask, Lorraine, you guys all hear me okay, right? Hello?
Yes, I was on mute. Your sound is great.
Great. I just want to make sure, I could just be talking for 15 minutes and be disconnected and not know it. So,
That has
very good.
happened.
Okay, very good. Thank you, Lorraine. Okay, so good. So now I'll talk just a little bit about petascale visualization and kind of the challenges that we have now. It's kind of a way of contrasting it with exascale visualization and the challenges that are going forward. And so with petascale visualization, there's really two sets of challenges. One is to design scalable algorithms. And so here we have two visualization techniques. In the slides, the one on the left is isosurfacing. So it's finding a surface of constant value. And the one on the right is called streamlines. The idea with streamlines is that you take particles, here they're at the little inlet at the bottom of the image, and then you displace the particles according to the velocity field, and you plot the trajectory that the particle would follow. And so as it turns out, the one on the left, isosurfacing, is actually a really easy thing to do in parallel. Every processor takes its piece, it operates on that piece, and it doesn't really need to do coordination with the other processors. The one on the right, streamlines, is actually a really difficult one to do in parallel because if you decompose over the pieces of the data set, then you might end up with some pieces that have many, many particles and they're doing all the work while the other processing elements starve for work to do. And if you do other parallelization schemes, they're similarly prone to starvation. So on the left, easy, on the right, hard. And so as a community, we've looked at scalable algorithms for the cases on the right. However, the other thing I think we've put a lot of attention into so far is how to minimize I/O. And the reason we've been so concerned about minimizing I/O is because for most of the operations we do, we typically spend almost all of our time reading data from disk. And so the claim here on the next slide is that it's almost always the case that more than half of the time is spent doing I/O, and sometimes like 98% of our time is spent doing I/O. So I/O is our bottleneck. The other comment that I want to make is that the amount of data we have to visualize is typically proportional to the total memory on the supercomputer. So if someone's running a simulation, they typically make a mesh and they typically size their calculation so that the mesh size and the variables will just barely fit into memory. And so the amount of data that we have to visualize, maybe we don't have to visualize all of the variables, but the amount we have to visualize is proportional to the total memory. And so as a result, what we're really concerned with is what's called relative I/O. It's the ratio of total memory and the I/O bandwidth. And so looking at the 2 points up above, it says how much data do you have to read and how fast can you read it. So if someone asks you to read 10 gigabytes of data and your disk can serve up 100 megabytes per second, that means that you can read the data in hopefully 100 seconds. That's probably too long when people are talking about interactive visualization. Alternatively, if they ask you to read a terabyte, but the disk can serve up 200 gigabytes per second, then that would only take 5 seconds, and that might be acceptable. So again, it's not how much data you have to read, it's not how fast you can read it, it's really the ratio of the two, and that's why we're so interested in relative I/O. And so the point is, if we consider a terascale machine, what we were dealing with before we got to the petascale era, as one that was relatively in balance, the petascale machine is out of balance. So the flops are going way up, and the memory is going up, but the I/O is not going up at the same rate. And so something that was already our bottleneck, we were already spending maybe 98% of our time reading data, has now gotten worse because the data sets are going to be bigger and bigger, but our ability to read them while it's going up is not keeping pace. And then looking forward to the exascale part of the talk, this trend is just getting worse and worse. So you can imagine each of these being squared, and the memory is going up, and the I/O again is not keeping pace. And so here's a slide that just supports that point some. It's a look at some of the #1 machines from 97 to 2008. So this is already kind of a dated slide. But you can see the trend in terms of how much time it takes to write memory from the compute nodes to the disk is getting worse and worse. And so as a result, the visualization community has known that we need to de-emphasize I/O in our approaches. And so I want to get to a point where I want to pause the talk real quick and make a really key point. And the key point is that petascale and exascale are different. And so I'm someone who has given talks about petascale visualization challenges and exascale visualization challenges, and it makes me feel sometimes kind of like a professional fearmonger, the boy who cried wolf. And so I want to point out that there really is a wolf at the door with petascale visualization, and it has to do with I/O. And the point is, I'm now going to talk about exascale visualization, and now there are a lot of wolves at the door. And we can name these wolves again, with petascale visualization, we have this I/O problem, and we still have that problem with exascale visualization. But, and again, this is the key point for as we move forward in the talk, the exascale uh, machine has a second wolf that's really scary, which is called the data movement wolf. And it's going to restrict a lot of what we can do on the machine. And depending on how you look at that data movement wolf, there's a lot of different facets to the problem. And so I refer to those facets as the data movement wolf's 4 angry pups. And so I'm going to tell you about the data movement wolf and its angry pups. And I'm going to do it again as a way of justifying to all of you when I tell you we need to work together, when I tell you, oh, life is going to be worse on the exascale machine than it was on the petascale machine, it's important that I say why it is. And so this part of the talk is really describing why it is and why it is that it's going to be so much worse and we need to work together to solve the problem. So I do want to comment for both of these problems, for the I/O bandwidth problem and for the data movement problem, in situ processing is a solution. And so in situ processing is really a key concept going forward when you're talking about HPC and visualization. And so the idea behind in situ processing is that you couple the visualization and analysis routines with the simulation code. So there's no I/O. And so you don't write data to disk. Instead, what you do is if you want to visualize and analyze data, you hand it off to the visualization and analysis routines. So what's good about this? Well, certainly there's no I/O. I just finished telling you about how we spend so much of our time doing I/O. And how slow it is. And so all of a sudden we've taken I/O out of the equation. That's fantastic. Another thing that's good about it is you can access all of the data. Typically people save out maybe 1 out of every 100 cycles or 1 out of every 500 cycles. And so then all you can analyze is that much data. And so with in situ techniques, you can actually access the data every cycle if you want to. Another thing that's good about it is you're running on the supercomputer while the simulation's running, and so there's a lot of computational power available. So those are the good things. There's a lot of bad things about in situ processing as well. So one bad thing about in situ processing is must know what you want to look for a priori. So if you run a simulation and then you're looking at maybe some movie that was produced using in situ visualization, and you see a hotspot and you want to know how that hotspot occurred, you have pretty limited controls to go back in time and check out what the conditions were for this anomaly to occur. If you didn't build it into the visualization and analysis that you wanted to perform before the code started, you're probably not going to get it. Another thing that's bad about it is it's an increasingly complex system. So it's already hard enough to build a parallel simulation code that you can run on these massive supercomputers. But now you have to get a whole nother player, the visualization and analysis routines, built into your system, and that makes it obviously more complex. Another con is constraints. So, for the visualization community, we think about running our program, and if they take a little longer, it's okay. And if we don't have enough memory, we say we'll just run again with more memory. But now all of a sudden we have to design algorithms that work within the constraints of how much memory the simulation code can afford, a time budget that they can provide, not increasing to network contention, and power. Power is a key theme in Exascale, and being able to carry these algorithms off with a power budget that won't blow the overall power budget for the simulation. Okay, so exascale computing. So there's kind of some rules of thumb that have evolved around the notion of exascale. And so these are the rules of thumb. One is, of course, it'll be capable of doing more than one exaflop. If not, it wouldn't be an exascale machine. The next is that the machine will cost less than or equal to $200 million. The thinking is that no funding agency is going to be willing to pay more than $200 million. The next rule of thumb is that the power budget is going to be less than or equal to 20 megawatts. And so that actually is really the key constraint. And so why 20 megawatts? My understanding is that 1 megawatt of power for a year costs about $1 million. And so a 20 megawatt power budget means that an agency is signing up to pay a $20 million a year power bill. And the thinking is that no agency wants to pay more than $20 million a year to power a supercomputer. And then the next assumption is, well, this is a moving target. Is it going to arrive in 2018? We've been hearing 2020. We've been hearing 2022. We actually don't know as a community. We've been planning for things that are coming on the nearer end, but that may or may not happen. Regardless, even if it's 22, that's not all that far away, and we need to be planning ahead in terms of how we're going to be able to exploit this machine when it arrives. So this slide comes from Pete Beckman at Argonne. It's a little bit dated, but I love the slide. Pete's a creative guy, and I love the title here. He says, Exascale is a heterogeneous distributed memory, and this is the part I like, gigahertz, kilocore, meganode system. So gigahertz refers to the clock speed, kilocore refers to the number of cores per node, so that means thousands of cores per node, and meganode means there's going to be about 1 million nodes in the system. And so Pete contrasted the number one machine in the world in 2009, which was the Oak Ridge Jaguar machine, with an exascale machine that could be arriving in 2018. And so this is really the heart of the story here, is that the Jaguar machine was able to do about 2 petaflops, but it took 6 megawatts of power to do it. And the exaflop machine that we're talking about, so this is 3 orders of magnitude more in computing power, had a limit of 20 megawatts. And so we only had 1 order of magnitude more power to be able to create 3 orders of magnitude more computational power. So that's really the heart of the challenge, is that we need to become 100 times more energy efficient as we do our computing. And so as a result, really everything on the that's running on the supercomputer needs to be rethought. And of course, the architecture itself needs to be rethought in a way that minimizes energy consumption. Some other interesting things to note, although there's going to be on the order of 1,000 times more compute power, there's only going to be 100 times more memory on the machine. And the concurrency is going up by a factor of potentially 10,000. So where there were 225,000 cores before, we're talking about 1 billion cores on the exascale machine. And so just making 1 billion cores all work in a synchronized fashion, do something productive is of course a really, really daunting challenge. Now, one thing I also want to point out is that I got finished telling you about the petascale machine and how it was out of balance between memory and I/O. Here we see that the memory is going up by a factor of 100, but they claim the I/O is going up by a factor of 100 as well. And so that would actually not be aligned with the slides that I just presented. The reason that it says this is because this is the expected rate in terms of how long it will take to write data. And the idea with the I/O subsystems is that they're actually going to build flash nodes onto every compute node, flash drives onto every compute node. And so as the simulation wants to write to disk, it's going to write to the flash drive. And then over a period of hours, the flash drive will slowly trickle that data down to the parallel file system. So the O of 100 speed up that you see here is really talking about writing to the flash drives. When it comes to reading the data, you won't see anything close to this. And this divide I was telling you about, the ability to produce data and the ability to read data, is going to continue and be much worse at the exascale. So there are 3 slides that try to motivate why this slide makes sense. And this is the first slide. This slide asks the question, if we have a gigahertz processor that takes 1 watt to power, what's the best way to be able to get and this can produce 1 gigaflop, what's the best way to produce 4 gigaflops? And so the idea on the bottom is that we quadruple the clock speed. But the problem is that the power consumed is proportional to the frequency cubed. And so if you had an approach like that, it would take, instead of taking 1 watt for 1 gigahertz, it would take 64 watts for 4 gigahertz. The idea on the top says that rather than increasing the clock speed, we could get more of these cores. And so again, we're getting 4 gigaflops, but we're doing it using 4 cores. But now instead of taking 64 watts, because the power is proportional to the frequency cubed, it would just take 4 watts. And so the result of this is that we don't want faster and faster clock speeds. What we want is we actually want slower clock speeds and more cores. So as we talk about having a billion cores, this is a big reason why. This slide is kind of a placeholder for a much bigger set of problems, which is the problem of the feasibility of an exascale machine. This looks at 3 different memory technologies and asks the question, if we wanted to get 16 petabytes of memory, 32 petabytes of memory, 64 petabytes of memory, 120 petabytes of memory, or 256 petabytes of memory, so 5 different total amounts of memory on the machine, how much would it cost? That's the y-axis for these 3 different memory technologies. And so you can see this one at the bottom, the green one is the cheapest. The one in black seems to be in the middle, and the orange one seems to be at the top. And this red line is the line that denotes $100 million. And so that's half of our total budget. And so if you think about the feasibility of just procuring an exascale machine, you probably don't want to spend more than half of your budget on memory because you still need money left over for the network, for the I/O subsystem, for the flops, and for other stuff. So half is probably the point where you say, I don't want to spend more than half of my money on anything. And so if you need 64 petabytes of memory, which is what the community is saying they need right now for it to be a useful machine, then really there's only one memory technology that's viable. And so this slide is kind of a placeholder of the larger issue, which is there's a very complicated trade space between different architectural components that you have to feel through to try to find a feasible system where you can afford everything you want and still fit the constraints of having a $200 million system and an exaflop total. Now, this slide is actually, it's a confusing slide, but I think it's one of the most important slides in the talk. This slide looks again at 3 different memory technologies, and it asks the question, how much many watts does it take for these what's called byte to flop ratio? And so the way to read this is if you're able to perform 1 flop for every 2 bytes you read in, so this is the one on the furthest right. I hope everyone can see my cursor moving around. If you can perform 1 flop for every 2 bytes reading in, then this memory technology, the amount of power it will take to move data from cache to registers will be 65 megawatts, which of course is not practical. If instead you're able to do 1 flop for every byte that you read in, then it will drop to 32 megawatts. And if you can do 2 flops for every byte you can read in, so this is the 0.5, then it will drop to about 17.5 megawatts. And so for this technology, if you can do 10 flops for every byte you read in, then it's gotten to be a pretty small number in terms of the overall power budget, which again, we do not want to exceed 20 megawatts. So this blue curve is the best. The worst one is the one that's at the top and left. I guess I'd call it kind of green. With that one, if you do 5 flops for every byte you read in, you're still at like 48 megawatts. If you do 10 flops for every byte you read in, you're still in the low 20s. And it's not until you do 100 flops for every byte you read in that you're actually getting well below this 20 megawatt line. And the problem, of course, is if we go back to this previous slide, we talked about 3 different memory technologies and how we're going to possibly be stuck with one. Well, guess what? It's the bad one. And of course, technology changes over the years. What's affordable changes, and so on. But I guess the point is that we have so much memory on the machine, and it's costly to do these memory moves from cache to registers. And in the context of having 1 million nodes, and the context of moving 64 petabytes of memory around, the energy costs add up very, very quickly. And so that's where this data movement wolf comes in. And this is the part that the entire community needs to be thinking about and reorienting around. How can we minimize power at every step? So here's a summary of the exascale challenges. The hardware architecture is going to be different than the petascale. It's not going to be multi-core, which is what we're used to, where you have tens of cores per node. It's going to be many-core, where you have hundreds or thousands of cores per node. And the way that you program something like that, it's not just a quantitative difference, it's a qualitative difference in terms of how you achieve efficiency on a many-core machine. If we're going to achieve an exaflop with $200 million and 20 megawatts, there are complex trade-offs. And data movement is going to be a key issue for everybody, but certainly for exascale visualization. So this likely means the end of traditional post-processing due to the I/O constraints, due to the costs of moving data around the machine. And even if we're not running a disk, even movement around the machine will be hard. And so at this point, we've summarized kind of what the exascale challenges are. And so what I'd like to explore for the remainder of the talk is what are the ramifications for visualization? So I think I mentioned earlier that I refer to this as the data movement wolf and its four angry pups. And these are the four angry pups. And so I'll go through them one by one. And so the first is how are we going to execute this in situ? I had a slide earlier about in situ processing. Mentioned that we didn't use the disk, there was no I/O, but there's actually a variety of ways to actually achieve in situ processing. And so one method would be what could be called tightly coupled in situ, where there's a simulation code. Each one of these squares is a compute node on the exascale machine that's running many different physics packages and also running various services, one of which could be Viz. And so it could be that the Viz and analysis routines are compiled into the simulation code, and the simulation code advances and it's having the visualization routines execute maybe at the same time, maybe after it's done executing, but executing on the nodes that it primarily occupies. Another idea is that the physics code runs on some dedicated nodes, and then there are some other nodes that are dedicated to visualization and analysis. And so in that case, we could actually have different architectures. It might be that the architectures for the node, the four squares on the left, are the architecture for the exascale machine, but maybe we have special high memory nodes that run Linux on the right to look at the data there. There's, of course, I think Oliver Krylos spoke last week and talked about the cave, and so he does great work there. And certainly there could be some notion that the data is being triaged out of this environment into maybe some dedicated cave type resource. This last configuration is what's called a hybrid in situ technique, where you triage the data as it sits on the compute nodes, and then you take the result of that triaging and send it to some dedicated viz and analysis job, which it can minimize data movement, but also not keep your simulation code held hostage while you maybe want to do some more intensive visualization and analysis routines on the data. And so the point of this is that there's lots of different in situ designs in play, and as a community, we actually don't know which ones are best. And there's a conversation to be had between the application scientists like yourselves and the visualization scientists like ourselves in terms of which one is best. Um, and so here are these three techniques again, and they all have negative aspects. If you run as part of the simulation code, you're memory constrained. Of course, it's very scary to me to think that the routines that I write, if they crash, they'll crash the overall simulation. But the loosely coupled one, the one where my visualization code runs on separate resources, well, there's data movement costs there, and you have to allocate resources for me. And the hybrid scheme is very complex. We have stuff running on your nodes, we have stuff running on my nodes, but maybe this is the way that we can minimize the data movement costs and still enable the things that people want to do. So there's actually quite a big conversation to have in terms of what the best ways are to carry out in situ techniques. And this conversation is not just a conversation that could be had today between all of you and myself. It's a conversation that's playing out throughout these communities, and there's actually been quite a bit of work in the in situ space recently trying to explore which approaches are the best and why. The next thing I want to talk about is programming languages. And so I know with the work I've done with the Visit visualization tool, we've really benefited from having a community visualization library called VTK, the Visualization Toolkit. It's developed by many, many people, and it's used by many, many people. It's been a very substantial investment, but it's all written in C++ for a single thread, and it's actually really mismatched for the exascale future in the mini-core environment. And so we're going to need something like this for the exascale. There are some really exciting projects that are underway that are trying to solve this problem to be the VTK for the exascale environment, but they're going to be a substantial investment as well. They need to be lightweight, they need to be efficient, they need to be able to run in a mini-core environment. And a problem that we have as a community, which is the same problem that you all will have when you want to run on the exascale machine, is how to even get started. Do you write CUDA code because you think it's going to be NVIDIA GPUs on the supercomputer? Do you try to write at a higher level, like a domain-specific language or DSL? OpenCL is supposed to be a portable language, and yet it doesn't seem like it's had a lot of adoption. Like maybe the language isn't quite there yet, although it seems really promising. So, as a community, as you want to go and rally and start preparing for the exascale machine, it's hard. It's hard to figure out exactly what to do. The next thing I want to mention is memory footprint. And so I'm actually going to go quite quickly through this slide. But I just want to say that we as a community, the visualization community, haven't done very well so far in terms of when we link in situ with a simulation code. We have our own ways of thinking about things, and we want to take the data that you have, and we want to allocate large arrays and translate a data from a format you understand to a format that we understand. And we need to do better than that. We need to have so-called zero copy in situ, where we don't copy the data, but instead work on it in the format you like. This slide is actually just a placeholder for a much bigger problem. And the bigger problem is that if we're running in situ, you all will have constraints. You want us to fit within the constraints of the time that you have allocated for us, the memory that you can allow for us, the network traffic that you can allow us to perform, and not create too much contention with the other things that you want to do on the network, and the overall power budget. The things that we do have a power cost, and we need to fit within your constraints. And so the new world it's a world of constraints, and memory is just one of those constraints, and we need to be able to execute efficiently within the constraints that you have. Now, the last one is the one that I think is the most exciting, and it's the notion of how do we do exploration at the exascale. And so I mentioned at the beginning of the talk that we had three primary use cases: exploration, confirmation, and communication. And so I would argue that, as a rule of thumb, confirmation and communication are things that can be done in situ. You know what you want to do a priori, you can program them in, and you can carry them out in situ. But with exploration, it's a lot harder. If you think about wanting to do exploration, I guess one modality would be that you could run the simulation, you could be monitoring what's going on, you could see something funny, you could pause the simulation, and then a human being could enter the loop and start asking questions and exploring what's going on. But that's tantamount to holding the exascale machine hostage. This is a very expensive resource, and I don't think that's what's going to happen. I don't think that we're going to pause the simulation so someone can interrogate the data. I think that it's such a valuable resource that needs to march on and advance the simulation at every moment. And so we have to ask ourselves, how are we going to do exploration? And so as a community, we're still scratching our head. I think we know what this should look like. What it should look like is there's an exascale simulation, and then there's some sort of in situ data reduction routine. So there's something running on every node that's taking the data that's interesting, and it's reducing it. So you can talk about reduction or compression, but somehow we're taking very large data sets and we're making them into smaller, tractable data sets, and that's what we write out to disk. And then we explore it after the simulation has run, much like we have for the last 20 years. But the tension is a tension between the reduction rate, the compression factor that you can achieve, and the integrity of the result. And so if you compress it as much as you possibly can, maybe you've lost so much integrity that the output is meaningless. But if you don't compress it enough, maybe you have high integrity, but you haven't achieved enough of a reduction. And when I say compression, gzip compression is a good thing to think about, and if that works, fantastic. Our community has thought about other things. We've thought about subsetting, so just finding the regions that are important. We've thought about multi-resolution techniques. We've thought about topological reductions. We've thought about a lot of things, and we're at the point right now where we're exploring which techniques work best in terms of this trade-off between compression and integrity. Um, and I'd actually say, Lorraine mentioned at the beginning that I won the Department of Energy Career Award. This is exactly the problem that we're trying to explore. And what we want is we want to create a cookbook for exascale scientists where they can understand the trade-offs between these different techniques and how much time they take to carry out a billion-way concurrency, what are the power costs, what is the loss of data integrity, and how can we communicate the loss in data integrity. And so I think it's a really exciting project and one we've had a lot of fun with for the last couple of years and will continue to work on through 2017. Underrepresented topics in this talk, there's a bunch, quintillions of data points, millions of pixels. Clearly we need scalable visual metaphors. The data is going to be very different at the exascale in terms of we're going to have ensembles of runs. There's going to be many physics packages integrated at once, and so the inputs to visualization software, the outputs of visualization software will be different. And then a problem that we have in common with everyone else who runs in HPC environments, the CPU software that we know and love and use, our legacy code, how we're going to make this work on a GPU, and really that should say on a many-core device. And then also resiliency. So I didn't mention resiliency at all, but fault tolerance is predicted to be a big issue at the exascale, and so we all have to be thinking about how to do things in a fault-tolerant way. Okay, so this talk was billed as exascale visualization, why things will change for you. And so my hope is that people, that people will understand now why when I come to you and say, oh, we need to do things in a way that's less good for you than what you've had before, you understand what some of the motivations are. So specifically what will change is you talk about the exascale. It's almost certainly the case that applications are going to need to run in situ. And it's almost certainly the case that applications need to think about how to compress or reduce their data for later exploration. And so both of these are going to require a partnership between application scientists and visualization scientists. What are the in situ models that work for you? What can we make work on that side? And in terms of how to compress data, I mean, that's a domain-specific thing. And so there's probably the best ideas about how to compress data will come from the application scientists like yourself. And then there's some other things that this will only work if the visualization scientists do their part. And so we're actively working on making usable code that can run in a many-core space and fitting within the constraints of the exascale simulation, including memory, time, power, and the network. And so these four sub-bullets, the four blue sub-bullets, all correspond to the angry pups that I put out earlier. So I think I've actually done okay on time. I think we came in pretty close to 50 minutes. And so I want to thank everyone for calling in and hearing about exascale visualization, and I'd be happy to take any questions.
Thank you, Hank, for that really exciting talk on exascale visualization. It's really interesting to hear all the challenges that we're going to have to solve to be able to visualize our simulations. If you have any questions for Hank, please go ahead and type them into the chat window.
Lorraine, would you like me to switch so I can see stuff in the chat window as well?
Yes, that'd probably be the easiest.
Okay.
So you have one question. You did. Okay, while we're waiting for questions, I just want to do a short advertisement for our next webinar. Our next webinar will be on March 13th at 2 p.m. And this will be quite a change of pace from our usual talks. Next month we'll have our UC Davis University librarian, Mackenzie Smith. Mackenzie leads the eScience Institute in helping research libraries to develop strategic plans to support digital research data curation. She also has worked extensively on intellectual property policy for scientific research data and on advocacy for open access to scholarly journals and other research products. Excuse me. Okay, Eric has a question for you. Do you see that?
Hey, Lorraine, I'm sorry. I can no longer see the session, and I tried opening up a second one, and when I did, it started playing your voice twice, and there was feedback, so I had to put it away. Would you mind reading the question for me?
Yeah, I thought it was just the cold echoing in my head. Yeah. The question is, it seems you weren't positive on user interaction with the visualization while the simulation goes on. Can you go into more detail on why this wouldn't work in your view?
Yeah, sure. That's an excellent question. So I guess this is a really expensive resource. It's $200 million, and so what we'd like for it to be that the simulation is advancing the entire time. What we have right now is we have the case that simulations can store data to disk. And when we have questions that take a long time to explore, we can look at the snapshots in time of the simulation on human timescales, right? We have to, it's the scientific method in play. We have to, we devise theories, then we design experiments that confirm or deny that theory, and then we use visualization and analysis tools to confirm or deny the hypothesis. And so that human timescale is one that's just too slow for the exascale machine. So anything where we want to explore data, I believe we're going to need to have ways that we can do that after the simulation runs. Now, I probably said it a little bit too harshly, and I would say that I think it's certainly possible to, at least I said it too harshly during the talk, I think it's certainly possible to be able to have a view of what's going on in the simulation and be able to do some pretty simple explorations of the data where maybe we make certain plots and we can change the view and look at them. And if we decide that the simulation is not doing the right thing, we should certainly stop it, right? This mandate that the simulation be progressing forward only makes sense if we think we're running the right thing. So I do think it's possible to have user interactions where we do, I guess people would call it steering, where we're monitoring what's going on. But I think that will solve some of our problems, but it won't solve all of our problems. And so I guess one of the points I want to make is it wouldn't solve the problem where we have to go and ask these questions that involve very, very involved explorations that are on human timescales that, like with this Rayleigh-Taylor simulation I talked about at the beginning, took months to actually figure out what the right questions were to ask and how to answer those questions.
Eric says thanks. John Louis has a question. He's asking, simulation results are sometimes archived as data. Will we need a similar change of heart in our expectations of our data centers?
Yeah, so simulations are saved as data, and so the second part, so it said simulations are also stored as data. It says, well, we need to have a change of heart in terms of how we store it in our data centers. Is that the question?
Yes.
And so yeah, I think so. So I think that this is another axis that we're going to have to give a lot on, and I think this is something that probably people on this call know pretty well. You run a simulation on one machine, and maybe the disk is pretty good, and so you save out maybe a snapshot in time of your simulation every 100th cycle. But then you go to another machine where the I/O subsystem isn't good, and gosh, you could find that you're spending almost all of your time doing I/O. And so what do? You maybe save out less frequently. Maybe you save out every 200 cycles. And so this trend is a trend that you'll see on more and more supercomputers, which is the I/O subsystems not keeping pace, and you have to save less and less frequently. And so, for the disk rates they're talking about in the exascale machine, the possible save rate is, very poor, and so poor that, I think people will have to innovate new ways. So, for the part that I think is one of the problems, challenges I think is really exciting, is this challenge of how can we, what new forms can we derive that, let us ask the questions and answer the questions that we want to know, but maybe don't look like storing out the full resolution mesh in all of the variables. It might be subsetting, it might be coarsening like a Google Maps, it might be saving out topological representations. There are a lot of ideas, but we need, but I think the right answers will often be domain specific. But I think across the board, people are going to have to give and save out less than they have before, and they're going to have to think about a lot about what they do want to save because they're definitely on a budget like they never have been before.
It definitely sounds like some trade-offs there.
Yeah. So as a researcher, it's really exciting. As a user, it's really scary.
Thanks, John. John's commenting that it's also a change of heart for our funding agencies, too.
Yes. Yes. Well, so I know that in some communities, the best way to get funding is to say that you want to run at very high concurrency, and so maybe there's other partnerships here that people can talk about, ways that they can bring some of these computer science ideas into what they're doing, and it might increases the chances for funding. At least we computer scientists like to think that we have value add in getting proposals funded.
Definitely. Well, great. I don't see any more typing, barring any sort of last flurry of activity here. I want to thank Hank once more for his time and for really laying out really nicely what the challenges are going to Exascale. With that, we'll see you next month, and have a good afternoon.
Okay, again, thank you, Lorraine, and thank all of you for calling in.